Hello class, this is Ms. Riggins, and today we're going to be talking about special right triangles. We've been working with right triangles for a long time, and we know that there are triangles that have a right angle. But there are a couple of special right triangles because they have some interesting properties. So let's take a look at this particular triangle. What do you notice based off the side lengths? If you can see that two side lengths or the legs of the right triangles are equal, that's correct. And if we were to actually find the measurements of the angles, we could see that the angles are 45 degrees, 45 degrees, and 90 degrees. So we call this type of triangle a 45, 45, 90 triangle. And let's take a look at some very interesting topics or some interesting ratios that occur. So let's take the leg to leg ratio. If I were to take the leg to leg ratio, you can see AB over BC is going to be 1. Okay? And if I take a look at the hypotenuse to leg ratio, take the length of the hypotenuse, AC, and divide it by one of the legs, and I get the number value of 1.414. Well, what does that mean? Well, this leg to leg ratio being 1 means that the legs are the same. In order to get the length of one leg, I multiply the other leg by 1 to get that leg. And what this ratio says for the 1.414, in order to get the length of this ratio, the length of the hypotenuse, I take the length of this leg and multiply by 1.414, and I will be able to get the length of the hypotenuse. Now, does that pattern always occur, no matter what type of 45, 45, 90 triangle we have? Well, let's see. Here we have a table of values, and as we can see, the first three values are the lengths of the sides of the triangle, and then the second two values are the ratios we just talked about as well. So let's go over here and change this triangle so it's a different size triangle, but it's still 45, 45, 90. Okay? And as I change it and just keep on taking a look at the very different values that I get, what do you notice changes and what do you notice stays the same? Well, if you said that what changes are the side lengths, you're absolutely correct. But what stays the same is the ratios. AB over BC is still 1. And AC over BC is still 1.414, even though the angle, and that's because all these different triangles are all similar to the same triangle because the angle measurements stay the same, which means that each of these triangles are similar to one another. So how is that of interest? Well, we have here a leg hypotenuse relationship, that if one of the legs is x, then the other leg is x, and the hypotenuse can be found by taking x, the length of one of the legs, and multiplying it by 1.414. And because that's the ratio that occurs each time when I divide the hypotenuse by one of the legs. But the question is, where does that 1.414 comes from? Well, if we take a look, and since this is a right triangle, we know the Pythagorean Theorem occurs. A squared plus b squared is equal to c squared. Since both of the legs are the same length, we kind of call them x. And this becomes x squared plus x squared is equal to c squared. And 2x squared is equal to c squared. And to figure out what c is, we take the square root of both sides. And I get x times the square root of 2 is equal to c. So the square root of 2 is actually approximated by 1.414. So another way that I can write this ratio, besides x times x, x and x times 1.414, is by what we call the 45, 45, 90 triangle relationship. If the leg is x, then the other leg is x, and the hypotenuse is x times the square root of 2, and that square root of 2 is approximated by that 1.414 that we see. This relationship always occurs for every 45, 45, 90 triangle. It doesn't matter what size the triangle is, as long as the angle measurements are still 45, 45, 90, this is the relationship that holds. As we can see here, no matter as I change the sides of the triangle, because they still remain a 45, 45, 90 triangle, this relationship still occurs. So now let's take a look at another special right triangle. In this case, if you take a look here at this triangle, we see that the legs are different lengths and the hypotenuse is not the same as any leg. And so, but if we take a look at the angle measurements, we see that it is a right triangle and that the two other angles are 30 and 60 degrees respectively. So let's take a look at the relationship between one of the ratios. Let's take a look at the relationship between the hypotenuse and the shortest leg. So if I take a look here, the relationship between the hypotenuse and the shortest leg, we see that the value of that ratio is 2. And if I take a look at, that 2 means that the hypotenuse is really twice the length of the shortest leg. So let's take a look at another ratio. Let's take a look at the ratio between the two legs. The medium leg divided by the short leg. When I take a look at that relationship, I get this, the value of the ratio as being 1.732. So let's see if that occurs no matter how many different ways that we change the size of that 30, 60, 90 right triangle. So as I change the size, it still remains a 30, 60, 90 triangle. And as you can see, the side lengths of the triangles are changing. And as they change, what do you notice stays the same? And if you notice that the hypotenuse to short leg ratio still stays the same as the same value of 2, which means the hypotenuse is still double the shortest leg, you are correct. And if you notice that the ratio between the medium leg and the short leg stays to be 1.732, that means that the medium leg can be found by multiplying the short leg times 1.732. So here we have a ratio, let me move this over. Short leg, medium leg, hypotenuse ratio. And in this case, if the short leg is x, then the hypotenuse is 2 times x, as based off this relationship, and the medium leg length is going to be whatever the short leg is times 1.732. Now, how do we know which is the short leg and which is the long leg? If I didn't have the angle measurements, how could I figure out which was the short leg and which was the long leg? Well, of course, that's obvious because of the fact of we have all the lengths and we can see the smallest length is the short leg. But what if I do have the angles? Where do you notice the shortest leg is across from? Well, angle EDF, which is this angle right here, is the 30 degrees, and that's the smallest angle of all the angles, and that's across from the smallest side. And then, of course, the longest length of the triangle is the hypotenuse, and that's across from the 90-degree angle. And then the medium leg is across from the 60-degree angle. So there's a relationship. Hopefully you remember from last semester that the smallest side is across from the smallest angle, and the longest side is across from the largest angle. So what does that mean for me? So this is a very important relationship. If the short leg is really half the hypotenuse, or the hypotenuse is twice the short leg. But let's take a look at what this 1.732. Why is it 1.732? Well, using the Pythagorean Theorem, a squared plus b squared is c squared, if we let a be the short leg length and c be the hypotenuse, which is we found to be double the short leg length, we get x squared plus b squared is equal to 2x squared. Well, 2x squared is 4x squared. So if I want to get b by itself, b squared by itself, I subtract x squared from both sides, and I get that b squared is the same as 3x squared. And then when I figure out what b is, I take the square root of both sides, and I get that b is equal to the short leg times the square root of 3. So if you kind of figured out that the square root of 3, if I were to put that in the calculator, that value would be approximated by 1.732. You're absolutely correct. So a better relationship to represent the lengths of the legs is what we call the 30, 60, 90 triangle relationship. Whatever the short leg is, if that's x, then the hypotenuse is going to be twice the short leg, and the medium leg length is going to be whatever the short leg is times the square root of 3. And those are our two very important problems. So in summary, here in our notes on page 111, we only have 2 theorems which we've talked about, and this is for the 45, 45, 90 triangle. The hypotenuse is always the square root of 2 times the length of each leg. So in order to figure out the hypotenuse, is x times the square root of 2. And in a 30, 60, 90 triangle, the hypotenuse is not the square root of 2 times the leg, but twice the length of the shorter leg. And the longer leg is the square root of 3 times as the shorter leg. And these are our relationships. And that's it.